Here is a scenario that has burned almost every team using AI coding agents. You type, "Build me a user dashboard with activity tracking." 40 seconds later, the agent returns 800 lines of polished, fully functional code. It compiles. Tests pass, and it is completely wrong. The agent built a real-time analytics dashboard with WebSocket connections, chart libraries, and a caching layer, when all you needed was a simple read-only summary page. Now you have two choices: spend hours unwinding the agent's assumptions, or throw it all away and start over. This is not a rare edge case. This is the default failure mode of every AI coding agent operating without a structured workflow. The agent did not fail because it wrote bad code. It failed because it wrote the wrong code with total confidence. And before this lecture is over, you will know exactly why this keeps happening, and the one structural fix that eliminates it. So why does this keep happening? The root cause is architectural, not accidental. AI coding agents are trained and optimized to produce code as fast as possible. The reward signal is generation speed and syntactic correctness, not alignment with unstated intent. This means by design, the agent treats every single prompt as a fully complete specification. There is no built-in phase for asking clarifying questions, no mandatory step to produce a requirements document, no checkpoint before the first line of code is written. And here is the compounding problem. The longer the agent runs without a spec, the more technical debt accumulates. Each autonomous decision, a library choice, a data model assumption, an API design, is built on top of the last unvalidated assumption. By the time you review the output, you are not reviewing code. You are adding a tower of silent decisions that will cost days to unwind. The absence of a spec phase is not a missing feature. It is a structural trap, and most teams do not even realize they have fallen into it until the rewrite is already underway. This is where Superpowers enters the picture, and it is worth being precise about what it actually is. Superpowers is an open-source plugin system, released under the MIT license, available right now on GitHub. It does not replode code, cursor, or codex. It does not patch the model. What it does is inject a structured development workflow directly into these agents before a single line of code is ever written. Think of it as a governance layer, a set of enforced phases that the agent must pass through in sequence. First, requirements clarification, then spec validation, then, and only then, implementation. The plugin works by providing a curated set of instruction files and workflow rules that the agent loads at session start. It is not magic. It is discipline, formalized and made non-negotiable. And because MIT licensed and fully open source, you can inspect every rule it enforces, fork it, and adapt it to your team's exact process. If it is instruction files, why does it actually work when plain prompting fails? That answer involves a specific architectural principle, and it is the focus of the next chapter. Let me make the contrast concrete, because the difference is dramatic. A raw AI agent, code, cursor, codex, take your pick, receives your prompt and begins generating implementation code within seconds. Over the next hour, it makes hundreds of micro-decisions autonomously. You come back to review, and you face the right problem we described at the start. Now run the same prompt through a Superpowers-equipped agent. The agent stops. It asks scoped, clarifying questions. It produces a written spec and waits for your sign-off. Only after you approve the spec does it write a single line of implementation code. The result? That same agent can now run autonomously for multiple hours, sometimes an entire session, without drifting from your intent. Not because the model changed, because the workflow changed. The discipline that senior engineers apply manually has been encoded into the agent's operating procedure. This is the transformation Superpowers delivers. And in the next chapter, we will dissect the exact three-law philosophy that makes this structure so robust. Here is what every AI coding agent does when left unsupervised. It writes the implementation first, and the tests never arrive. Not because the model doesn't know what TDD is, it can recite the red green refactor cycle perfectly. The problem is that writing tests feels like friction, and AI agents are optimized to reduce friction and maximize token output that looks like progress. Superpowers breaks this by making TDD a hard workflow gate. The agent cannot proceed to implementation until a failing test exists. RED is not optional. Green must be verified. Refactor is a named step, not an afterthought. This isn't a prompt suggestion. It is a structural lock in the workflow, and that distinction is everything. So why does Yagni matter just as much? You'll see in the next scene. Yagni, you aren't going to need it. Sounds obvious until you watch an AI agent in the wild. Ask it to build a user login endpoint, and you will get JWT handling, refresh token rotation, rate limiting middleware, an audit log schema, and 3 abstraction layers for a feature roadmap that doesn't exist yet. The model is pattern matching against every enterprise codebase it was trained on, and it defaults to maximum completeness. This is scope creep at machine speed. Superpowers enforces Yagni by constraining the implementation step to only what the confirmed specification describes, nothing more. If it wasn't in the approved spec, it doesn't get built. The agent cannot add nice-to-have infrastructure because the workflow has no slot for unspecified work. But over-engineering isn't the only silent killer. Code duplication is just as dangerous, and that's where DRY comes in. DRY, don't repeat yourself, is the third law, and it's the one most likely to be violated silently. When an AI agent generates code across multiple files in a single session, it doesn't maintain a global awareness of what it already wrote 20 function calls ago. It will copy-paste logic, re-implement the same validation in 3 places, and create diverging sources of truth that will bite you 6 months later when one copy gets updated and the others don't. Superpowers addresses this through its review skills, which run a severity-graded duplication scan before any merge is allowed. Duplication is flagged at 3 levels: advisory, warning, and blocking. A blocking flag halts the workflow entirely until the single source of truth is extracted. This turns DRY from a best practice into a merge requirement. And that combination, TDD, Yagni, and DRY enforced structurally, is the foundation everything else in Superpowers is built on. We go deeper into the philosophy behind how Superpowers decides what to build in the first place. Every failed AI coding project starts the same way: a vague prompt handed to a model that it is incentivized to start generating code immediately. Build me a dashboard becomes 10,000 lines of assumptions about data sources, chart types, user roles, and refresh intervals, none of which were specified. Superpowers has a dedicated broming skill that works on a completely different principle: the Socratic method. Instead of coding, it asks questions. Targeted, sequential, clarifying questions designed to extract a precise specification from whatever vague input you started with. The agent treats the prompt as a hypothesis, not a requirement. It probes for edge cases, confirms scope boundaries, and surfaces ambiguities before a single line of production code exists. The questions aren't random, they follow a structured extraction protocol that covers functional requirements, constraints, and acceptance criteria. But asking questions is only half the story. What happens after the answers matters just as much. Once the brainstorming skill has extracted a candidate specification, Superpowers does something that feels almost old-fashioned in the age of autonomous AI. It stops and asks for your approval. This is the design approval checkpoint, a hard workflow gate that requires explicit user confirmation before any implementation planning begins. No planning, no task decomposition, no code. Nothing moves until you read the spec and sign off. This sounds like overhead, but the math is brutal. Fixing a misunderstood requirement at the spec stage costs minutes. Fixing it after implementation costs hours. Fixing it after integration costs days. The checkpoint exists because AI agents are very good at being confidently wrong, and a 2-second confirmation is the cheapest insurance policy in software development. The confirmation itself becomes a contract between you and the agent, and the entire downstream workflow is anchored to that contract. But what does this checkpoint actually do to code quality at scale? That's the payoff we need to examine. Step back and look at what the Socratic brainstorming philosophy actually produces. A development process where requirements are explicit, acceptance criteria are defined before code exists, and the AI agent is operating against a confirmed contract rather than a guess. This is spec-driven development, and it is the single highest leverage intervention you can make in the quality of AI-generated code. Quality control measure, TDD gates, Yagni constraints, DRY enforcement, is downstream of this. If the spec is wrong, perfect test coverage just proves you built the wrong thing perfectly. The clarification first approach is what separates a Superpowers workflow from a raw Claude code session where the model confidently sprints in the wrong direction. These 3 laws, TDD, Yagni, DRY, enforced by structural gates, and grounded in a spec extracted through Socratic dialogue, form the philosophical core of the entire system. In the next chapter, we go from philosophy to mechanics, the 7 concrete skills that make workflow run, and how they chain together to handle real engineering tasks, from first prompt to merge pull request. Here is where Superpowers stops being philosophy and starts being machinery. The first skill is writing plans, and it is the foundation everything else builds on. When an AI agent receives an approved design, writing plans breaks it into atomic tasks, each one scoped to 2 to 5 minutes of real work. And here is the critical part. Every single task entry must include 3 things: the exact file paths that will be touched, the complete code changes to be made, and the verification steps to confirm it worked. No vague instructions like update the auth module. Instead, open src auth token ts. Replace lines 42 through 67 with this exact block, then run an npm auth to confirm the green signal. That specificity is what makes downstream automation possible. Without it, sub-agents guess, and guessing at scale is how code bases become graveyards. The writing plan skill is what separates a supervised assistant from a truly autonomous pipeline. But a perfect plan means nothing if all agents are writing to the same branch. That problem is solved by the skill coming next. Now imagine you are running 3 features simultaneously: authentication refactor, payment integration, and UI overhaul, all on the same working directory. Every agent is writing files, installing packages, maybe even changing configuration. The result is chaos, merge conflicts, overwritten work, and an environment that is in a permanently broken state. The using Git work trees skill eliminates this entirely. Git work trees let you check out multiple branches of the same repository into separate physical directories on disk simultaneously. Superpowers uses this to give every parallel workstream its own completely isolated workspace. Agent A is working in /worktrees/feature auth. Agent B is in /worktrees/feature payment. They share the same Git history. They never touch the same working files. This is not just a convenience, it is what makes true parallel development safe. No cross-contamination, no race conditions on the file system, no one agent's brocade bleeding into another's clean environment. But isolated workspaces alone do not make a pipeline autonomous. You still need something to actually run the tasks inside each workspace. That is where the third skill becomes the game changer. You now have a detailed plan and isolated workspaces. The third skill, subagent-driven development, is what turns those inputs into autonomous execution. Here is how it works. Superpowers reads the task list produced by writing plans, then spawns an independent subagent for each task entry. Each subagent receives exactly its task, the file path, the code, the verification command, and nothing else. Executes, verifies, and reports back. No subagent knows what the others are doing. No shared state, no context window, no cascading failures. This design means a single subagent failing does not halt the entire pipeline. The orchestrator logs the failure, isolates it, and continues with the remaining tasks. In practice, this architecture allows superpowers to run autonomously for several hours on a complex feature set without requiring human intervention on every step. Think of it like a factory floor. The orchestrator is the plant manager, and each subagent is a specialist worker executing one well-defined job. The plan is the assembly specification. The work tree is the workstation. Now, a perfectly executed plan that produces broken code is worse than no plan at all. That is exactly why the next set of skills exists. Here is the uncomfortable truth about AI coding agents, left unsupervised. They write code that passes a quick sanity check, but silently breaks edge cases. The test-driven development skill exists to prevent exactly that. It enforces the full red green refactor cycle. Not as a suggestion, but as a non-negotiable gate. Here is how each phase triggers automatically. RED phase. Before implementation code is written, the agent must write failing tests that define the expected behavior. If the tests pass immediately, the skill rejects them, because tests that never fail prove nothing. Green phase. The agent writes the minimum code required to make those tests pass. No gold plating, no premature optimization. Just green. Refactor phase. Once green, the agent restructures the code for clarity and maintainability. And the tests must still pass after every change. The cycle cannot be short-circuited. An agent that tries to skip RED and write implementation first will be stopped. This single skill eliminates an entire class of AI failure. Confident code that has never actually been tested. What happens when the code is correct but the logic is wrong, when there is a real bug to chase? That is a completely different problem, and it needs its own skill. Every experienced engineer has seen it. An AI agent encounters a bug, wraps the offending line in a try-catch, the tests go green, and the root cause is still sitting there, silently corrupting data or waiting to resurface. The systematic debugging skill is specifically designed to prevent that pattern. It enforces a 4-step cause analysis framework before any fix is applied. Step 1. Reproduce. The agent must produce a minimal, deterministic reproduction case. If it cannot reproduce the bug reliably, it cannot claim to understand it. Step 2. Isolate. Narrow the failure surface, eliminate variables until the smallest possible code path that triggers the bug is identified. Step 3. Hypothesize. Generate at least 2 competing hypotheses about the root cause, each with a predicted observable outcome. Step 4. Test hypotheses. Run targeted experiments to confirm or eliminate each hypothesis before writing a single line of fixed code. Only after completing all 4 steps does the agent write the actual patch. This framework does not slow down debugging. It prevents the exponentially more expensive cost of shipping a masked bug into production. But fixing bugs correctly is only half the quality story. The other half is making sure the code that reaches merge is actually what was specified. The code review skill closes the quality loop. with a two-stage review process that runs automatically before anything is considered merge-ready. Stage 1 is spec compliance. The agent checks the implementation against the original specification by line, not against its own interpretation, but against the actual written spec. Does the code do what was agreed? Are any requirements missing or misimplemented? Every finding gets a severity rating: critical, major, minor, or informational. Stage 2 is code quality review. Independent of spec compliance, the agent evaluates the code itself. Is it readable? Are there security vulnerabilities? Are there performance anti-patterns? Are naming conventions consistent? Again, every issue is severity rated and written into a structured report. The key insight here is that these two stages are deliberately separate. A piece of code can be perfectly spec compliant and still be a maintenance nightmare, and the reverse is equally true. By separating the reviews, Superpowers catches both classes of failure. And critically, this is not a soft suggestion. A critical finding in either stage blocks the pipeline. Now, all quality gates are cleared, the branch needs to land somewhere. The final skill handles exactly that transition. Every feature branch has to end somewhere. But end is not a single action. It is a decision point with multiple valid outcomes depending on team policy, CI status, and review state. The finishing a development branch skill structures that decision into a repeatable workflow so the agent never just silently merges or a branch. Here is the decision flow. First, are all quality gates passed? If any critical or major issues remain from the code review stage, the skill stops here and surfaces a human-readable blockers report. Second, is this a direct merge repository or a PR-required repository? Superpowers reads the project configuration to determine the correct path. If direct merge is allowed and all gates are green, the agent merges the worktree branch into the target branch and cleans up the worktree directory. If a pull request is required, the skill generates a structured PR description, including a summary of changes, the task list that was executed, and a link to the review findings, then opens the PR through the GitHub API. Third, post-action cleanup. The worktree is removed, the local branch reference is pruned, and the orchestrator marks the task set as complete. This is the moment where all 6 previous skills converge into a single committed outcome. Now, you have seen all 7 skills individually. The question is, how do they actually connect and fire in a live session without you manually calling any of them? Let us now pull back and look at all 7 skills as a single integrated system. Because the most important property of this workflow engine is one you have not heard me mention yet. You never manually invoke any of these skills. Superpowers determines context from what is happening in the session and triggers the appropriate skill automatically. Writing plans fires when a design is approved. Git worktrees spin up when parallel tasks are detected. Subagent-driven development launches when a plan is ready for execution. TDD activates when implementation work begins. Systematic debugging engages when a test failure or error is logged. Code review runs when a task set is marked complete. And finishing a development branch triggers when all tasks in the worktree have passed review. The skills interlock like gears. The output of one is the input condition for the next. This is what Superpowers means by a workflow engine. Not a collection of tools you choose from, but a state machine that advances itself. And here is the question this raises immediately. If this workflow engine is so powerful, why is it not already built to Claude Code, Cursor, or Windsurf? The answer is in the next chapter, where you will see exactly how to install and configure Superpowers across each of these agents, and why the configuration step is where most teams get it wrong. Let's get this installed. No theory, just the exact commands. You run one line. /plugin install Superpowers, sourced from the Claude plugins official registry. That registry matters. It's the verified source, not a random GitHub fork. After the install, Claude Code will confirm the plugin is active and list the 7 skills by name. If you don't see that confirmation list, something went wrong. We'll cover exactly what in a few minutes. The entire install takes under 10 seconds. But here's what most people miss right after install. The plugin doesn't just sit there waiting for you to call it. It starts intercepting your prompts immediately, and the first request you send will behave very differently than you expect. Cursor uses a slight different command syntax. That's intentional. Agent has its own plugin API, and Superpowers ships with agent-specific adapters. In Cursor, you type /add plugin Superpowers inside the Cursor AI chat panel. Not the terminal, the agent interface itself. Once installed, Cursor surfaces the skill set directly in its sidebar under Active Plugins. You'll see each skill listed with a toggle. Don't turn any of them off individually. The skills are interdependent. Disabling Brainstorm, for example, means the planning skill has no input context to work with, and the whole chain degrades silently. That silent degradation is exactly the kind of failure we talked about in Chapter 2. Now watch what happens when we install on Gemini CLI. Because the architecture difference that reveals something important of how Superpowers was actually designed. Gemini CLI takes a third approach. Gemini extensions install Superpowers. Extensions are Google's equivalent of plugins, and the install hooks directly into the Gemini agent runtime. What's worth pausing on here is that you just saw 3 different install commands for 3 different agents, and yet the skills behave identically across all of them. That's not an accident. Superpowers was designed agent-agnostic from day one, because the authors saw that the AI coding agent landscape was going to fragment. Teams shouldn't have to relearn their workflow every time they switch tools. One skill set, any agent. This is a strategic moat, and it's also why the MIT license makes commercial sense. The framework spreads freely, which means the ecosystem grows, which means becomes the core. That's the business model hiding inside an open source project. Up next, we testing the install output and actually verify the skills are firing. Because confirmation messages lie more often than you'd think. Installation output is not verification. Here's the real test. Send a deliberately vague prompt to your agent, something like, build me a user authentication system. No specs, no constraints, nothing. Before Superpowers, the agent would dive straight into code. With Superpowers active, the brainstorming skill intercepts that prompt and the agent responds with questions first. What auth method? Oath, JDT, session-based. What's the user model look like? That question first behavior is your proof of life. If you get code back immediately, the skill chain did not activate, and you need to troubleshoot before going any further. No configuration required to trigger this. No special syntax in your prompt. The interception is automatic. This is the zero config design philosophy. The best developer tools disappear into the workflow. But wait, zero conf means you can't always tell when something quietly breaks. That's exactly why the next topic matters more than people expect. Superpowers is MIT licensed. Full stop. That means you can fork it, modify it, ship it inside a commercial product, and build proprietary skill sets on top of the core framework without owing anything back. For individual developers, MIT means you can extend the 7 skills to fit your stack, add a database migration skill, a security audit skill, whatever your team needs repeatedly. For organizations, it means you can package a company-specific skill layer that enforces your internal coding standards across every AI agent your developers use. The community extension model is already producing specialized forks, one for data engineering pipelines, one for front-end component generation, one for infrastructure as code. The core stays stable, the ecosystem grows around it. This is the same pattern that made VS Code extensions dominate the editor market. And if you think that comparison is a stretch, consider that the authors explicitly cited VS Code's extension model in their architecture docs. That's not accidental inspiration. That's a deliberate blueprint for adoption. Let's talk about what breaks and how to fix it fast. The number 1 issue, agent version mismatch. Superpowers requires Claude Code version 1.4 or higher, Cursor 0.38 or higher, Gemini CLI agent runtime 2 or higher. If your agent is older, the plugin installs but the skill chain never initializes, and you get no error message. You just get a normal AI agent pretending to work. Second most common, plugin conflict. If you have another workflow plugin installed that also intercepts prompts, both plugins fight for the first interception slot. Resolution. Disable other workflow plugins, install Superpowers first, then re-enable others. Third, corporate proxy environments where the registry call is blocked by a firewall. Solution is to use the offline install package from the GitHub releases page. Check each of these 3 in order before spending time debugging anything else. This is the complete setup foundation, and in the next chapter, take everything we've configured here and put it to work on a real feature build from a blank file to a merged pull request. That's where the theory either holds up or falls apart. Here is the prompt that breaks most AI coding agents. Add a user notification feature. That's it. No scope, no constraints, no success criteria. A naive agent just starts generating files, and you won't discover the mismatch until hours later. The brainstorming skill intercepts this before a single line of code is written. It fires a structured quest sequence. What triggers a notification? Email, in-app, or push? What does delivered mean? Sent, or confirmed received? Who are the edge case users? Within 5 exchanges, that vague prompt becomes a locked spec both you and the agent agree on. The transformation isn't magic. It's a disciplined extraction process. And the moment you see the before and after side by side, you'll never send a vague prompt again. Once the spec is approved, the writing plan skill takes over. And this output is what separates professional AI-assisted development from chaotic prompt and pray sessions. The plan is not a vague to-do list. Every task has an explicit file path, the exact function or class expected to exist afterward, and a verification step the agent must pass before marking it complete. Look at this example. Task 2 says create notification service. File path is SARC services notification service spawn TS. Expected export is notification service class with a send. Method verifications unit test passes with mock transport. There is no ambiguity. The agent cannot improvise. And here is the critical insight. The plan itself becomes the contract. If the agent deviates, the verification step catches it immediately. Next, we'll see how these tasks get distributed across multiple agents simultaneously. Now here is where the workflow starts to feel genuinely different from anything you've used before. The subagent-driven development skill reads the approved plan and distributes independent tasks across multiple subagents, each one working in isolation on its own branch segment. T1 and T2 have no shared file dependencies, so they run in parallel. T3 depends on T2, so it queues. The orchestrating it tracks status in real time, running, completed, failed. If a subagent hits a blocking error, it surfaces it to the orchestrator, not silently swallowing it. No more the agent was working for 20 minutes and produced nothing useful. You see progress. You see blockers. You stay in control without micromanaging every line. And the next section reveals the one constraint that keeps every subagent honest, the TDD enforcement loop that makes failure impossible to hide. This is the RED phase, and it is enforced, not suggested. The agent is instructed to write the failing test file first and commit it to the branch before touching any implementation code. If it tries to write the service file before the test file exists in the commit history, the TDD skill blocks execution and flags a violation. Look at this test. It imports notification service, calls send with a payload, and asserts it returns a delivery receipt. Right now, that import will throw. The service file does not exist. The test is read. That is the point. The test is not a formality. It is the specification expressed as executable code. Every assertion in this file is a requirement the implementation must satisfy. No test, no code. That is the only rule. But here is what most developers get wrong about TDD. Writing a failing test is the easy part. The hard discipline starts in the next phase. Green phase. The agent now writes the absolute minimum code to make that test pass. Not the feature complete version. Not the optimized version. Look at the send method. It does exactly what the test demands and nothing more. It calls the transport, constructs the receipt, turns it. The test goes green. Then refactor begins. The agent identifies that the receipt construction logic is duplicated across send and the email fallback adapter. Under the DRY constraint, it extracts a build receipt, utility function, and updates both callers. Tests still pass. The refactor is verified, not assumed. This is the complete TDD cycle: red, green, refactor, executed under enforcement, not honor system. And what happens when this code goes to review? The two-stage review output will surprise you. The two-stage review skill runs after all subagents complete. Stage 1 is spec compliance. Did the implementation actually fulfill every requirement in the approved spec? Stage 2 is code quality. Does it meet the team's standards for structure, error handling, and maintainability? Every issue gets a severity grade. P1 is a blocker, P2 is a required fix before merge, P3 is a recommendation. In this example report, there is one P1, the email fallback adapter does not handle transport timeout. It was in the spec, it is not in the code. The agent cannot mark the branch complete until that P1 is resolved. PU flags missing error logging in the controller. PIT notes that the buildRET function could be moved to a shared utilities module. This is not a code review you have to run manually. It is automated, structured, and gatekeeping. And in the final chapter, we'll pull one of these pieces together into a workflow you can apply to your very next feature, starting today. Let's be direct about what actually changed in our workflow. For Superpowers, you were handing Claude a vague prompt and hoping for the best, and hoping is not an engineering discipline. After Superpowers, 5 concrete transformations happen. First, spec-first development. You never write a line of code until a structured specification exists. Second, thirst execution. Acceptance criteria are locked before any implementation begins. Third, task decomposition. Large features are broken into atomic, parallelizable units. Fourth, subagent delegation. Each unit is handed to a specialized agent with scoped context. No more context window pollution. Fifth, severity-graded review. Output is evaluated by impact level, not by line count. These 5 changes are not preferences. They are the load-bearing walls of a system that doesn't collapse under complexity. The question is no longer whether AI can code, it's whether your workflow is disciplined enough to direct it. And that discipline gap is exactly what we've been closing all lecture. Now zoom out. Every skill in Superpowers connects to every other skill. And that's not an accident, it's an architecture decision. The mental model looks like a closed loop. You start at the center with your feature intent. Branching left, the brainstorming skill and the spider skill convert that intent into a verifiable contract. Branching right, the task planner and subagent spawner that contract into executable work items distributed across parallel agents. The loop closes through the review skill and the merge validator, which gate output before it ever reaches your main branch. And sitting at the top, the context injector feeds every agent precisely the knowledge it needs, no more, no less. What you are looking at is not a collection of prompts. It is a self-reinforcing pipeline where each skill's output is the next skill's input. Remove any one node, keep all 7 connected, and you have something genuinely new. An AI development workflow that enforces its own discipline. That is the system you now know how to build. Here is your action checklist. Not aspirational, executable today. Step 1. Install Superpowers on your primary Claude Code agent before you close this tab. The GitHub repository is live. The README walks you through the install in under 10 minutes. Step 2. Take the next real feature you are planning and run the brain skill on it first. Do not any code. Just run the skill and read the output. You will immediately see scope you missed. Step 3. Write one custom skill. Pick a workflow pain point specific to your codebase, a linting convention, a deployment checklist, a schema migration pattern, and encode it as a Superpowers skill. That is system compounds. Step 4. Contribute it back. The project is open source and community skills are the multiplier that makes the entire ecosystem more valuable for every developer using it. The infrastructure is already built. The only variable now is whether you use it. And one warning, teams that adopt structured agentic workflows in the next 6 months will have a compounding productivity advantage that is genuinely difficult to close later. Back in the very first scene of this lecture, we opened with a question. Why do AI coding agents fail even when the model is brilliant? You've seen the answer play out across 6 chapters. The failure was never about intelligence. Claude Code is extraordinarily capable. The failure was about workflow discipline, the absence of an enforcement layer that converts raw capability into reliable, reviewable, mergeable output. Superpowers is that enforcement layer. It doesn't make Claude smarter. It makes your process smarter. And that is the shift that separates developers who get insistent magic from developers who get a production-grade, autonomous pipeline. The future of agentic development belongs to engineers who understand that prompting is not enough. Architecture is required. You now have that architecture. The only remaining question is what you will build with it.